Welcome to today's presentation on a critical intersection in modern industry. Can you trust industrial AI? My name is Santosh Raikar, and today we're moving past the hype. While AI promises transformative efficiency, its true value depends on a simple principle. It must be useful enough to act on and controlled enough to trust. We will explore how to manage hallucinations, false alerts, and most importantly, how to maintain engineering accountability in an automated world. The core of our discussion starts with a question often heard in the boardroom. When an AI system recommends action on a critical asset, who is accountable if it is wrong? While AI can certainly accelerate our decision-making process, we must remember that accountability is a human responsibility that cannot be delegated to a mathematical model. Our thesis today is fourfold. First, we shouldn't view industrial AI as just a tech category, but as an engineering decision system. Second, trust isn't a vague feeling. It's evidence based on validated data and known boundaries. Third, our biggest risk isn't that AI is imperfect, but that we might treat a model's confidence as equivalent to engineering proof. Finally, leadership must ensure the decision process remains safe and auditable even when the AI fails. Why is this urgent? Because manufacturers are rapidly scaling AI from small pilots into core operations. According to Rockwell Automation, AI-augmented operations are expected to jump from 34% today to over half of all operations by 2030. As AI moves deeper into production and risk decisions, our governance must shift from simple technology approval to rigorous engineering assurance. Today's agenda covers 6 key areas. We'll start with what leadership needs to understand about trust, move into the technical risks like hallucinations and false alerts, and then dive deep into governance, validation, and operational roadmaps. We'll conclude with practical case vignettes to see these principles in action. In part 1, we'll look at the foundation of industrial AI trust. We need to stop viewing AI as just another software tool and start seeing it as an integral part of the plant's operating system. It's important to realize that industrial AI is not a monolith. It covers everything from vibration anomaly detection and predictive maintenance to process optimization and quality inspection vision systems. More recently, we're seeing generative AI copilots for SOPs and agentic systems that can actually initiate workflows. Each of these requires a different level of trust. Trustworthiness is not one size fits all. It must be context specific. An AI searching through manuals has a much lower risk profile than an AI influencing a turbine trip or a boiler operation. Drawing from the NIST AI risk management framework, we must balance validity, safety, and explainability against the potential consequences of a failure. We often see an executive trust gap. While leaders see a strategic edge, plant teams might just see another source of annoying alarms. To close this gap, we must move away from reporting simple model accuracy and start providing clear, actionable information. What do I do? When do I do it? And what is the risk? Trust in industrial AI is socio-technical. Sensors and algorithms are only half the story. Work practices, authority, and training make up the rest. A perfect model will fail if the organization lacks the discipline to respond, and a weak model could be dangerous if it's hidden behind a sleek, authoritative-looking dashboard. Think of trust as a chain. It starts with data integrity and moves through model validation, decision thresholds, and field action, finally closing with a learning loop. If any one of these links is weak, say the sensor data is bad or the field execution is poor, the entire chain of AI confidence converts into operational risk. Board members should go beyond asking, do we use AI? And start asking harder questions. Which specific decisions is AI influencing? What is the maximum credible consequence if it's wrong? Who has the authority to override it? We need evidence that the system is actually improving decisions, not just generating noise. In part 2, we tackle the technical gotchas. The real problem with AI isn't just that it can be wrong. It's that it can be wrong with a high degree of perceived authority, leading us into a false sense of security. In the world of generative AI, a hallucination is a plausible but false output. In an industrial setting, this risk is amplified. An AI might suggest a maintenance priority that violates the laws of physics or ignore the specific operating context of a machine. These confabulations are dangerous because they feel authoritative. What does this look like in the field? It might mean an AI suggesting pump cavitation when the suction pressure is perfectly fine, or inventing a troubleshooting step that actually violates site safety rules. These aren't just bugs. They are fundamental failures of the AI to understand the physical world it is monitoring. We also have to talk about false alerts. They are not harmless. They drain resources, cause alert fatigue, where users start ignoring the system. It can even lead to unnecessary maintenance that introduces new defects. We have to manage both false positives and false negatives based on the actual consequences to the plan. Statistical accuracy is a deceptive metric. A model can be 99% accurate, but still fail on the 1% that matters most for safety. While the costs of false positives, like wasted labor, are visible, the costs of false negatives are often hidden until a catastrophic failure occurs. We need consequence-weighted performance metrics. This confusion matrix helps us categorize AI outcomes. We want true positives, real problems caught, and true negatives, quiet during normal operation. But we must specifically investigate why a model saw a risk where physics did not, or what independent safeguards failed when a model stayed quiet during a real failure. Avoid the overconfidence trap. A confidence score from an AI is a mathematical pattern match, not an engineering certainty. Leadership must demand uncertainty bands and operating limits. A 95% confidence score on a model trained on narrow data is significantly less valuable than a lower score on a robust, well-validated model. In the control room, we see automation bias. People tend to overtrust recommendations when they come from an authoritative-looking interface. Strong governance gives your team permission to challenge the model and requires the AI to show its work before any action is taken. Then there is data drift. A model that worked perfectly yesterday might be useless today if the product mix changes, the ambient temperature rises, or a sensor is replaced. Drift monitoring is not a nice-to-have data science task. It is an essential part of ongoing model integrity. Remember, bad data can still lead to confident AI. If you have wrong tag mapping or poor work history logs, the AI will simply learn the wrong lessons with high confidence. This is why data governance must be viewed as a reliability control, not just an IT clerical task. Finally, we must consider security. Industrial AI is a new surface for data poisoning and model manipulation. If an AI assistant has access to your sensitive manuals or can initiate workflows, it becomes a risk boundary that must be protected by the same rigorous standards we use for OT cybersecurity. In part 3, we move to the solution: engineering accountability. The rule is simple: AI can recommend, but a human engineer must verify, authorize, and own the final decision. If we translate the NIST trustworthy AI characteristics into industrial terms, we're looking for 5 things. Is it valid for this specific asset? Is it safe if it fails? Is the decision-making process transparent? Can an engineer explain why it's making a recommendation? And is it fair and secure? We recommend using ISO/IEC 42001 as a management system frame. This ensures that AI risk isn't just a technical problem buried in a model. It's a systemic responsibility that covers policy, roles, risk assessment, and continuous management review. We can't treat all AI the same way. We need consequence-based risk tiers. A low-risk manual search assistant only needs a user review, but a high-risk recommendation like an asset shutdown requires formal engineering sign-off, a change management process, and an audit trail. Accountability requires named human roles. We need a business owner to define value, a technical owner for the model lifecycle, an engineering authority to approve the technical basis, and an operations owner for the day-to-day use. Risk and audit teams then provide the final layer of oversight. Simply having a human in the loop isn't enough if that person lacks the time or authority to actually challenge the machine. For high-consequence decisions, the human must be a qualified technical authority with access to the evidence needed to make an informed choice. Before an engineer signs off on an AI recommendation, they should answer 5 questions. Is it physically plausible? Does independent data support it? What's the risk if the AI is wrong? What's the risk if we ignore it? And what field verification do we need before we pull the trigger? We must integrate AI into our existing management of change, MOC, processes. Even if no hardware is touched, changing a model's threshold or a data source is a change to the decision-making process and should be treated with the same level of scrutiny as a physical modification. A clear policy defines what is permitted, conditional, or restricted. While using AI for anomaly triage might be permitted, using it for safety-critical decisions without independent safeguards should be strictly restricted. A clear operating envelope is much stronger than a simple yes or no to AI. Traceability is key. We need an audit trail that documents everything: the input data, the model version, the recommendation, who reviewed it, the resulting action, and finally, what we learned from the outcome. This isn't just bureaucracy, it's engineering traceability. In Part 4, we focus on engineering validation. Trust is earned through proof, not promised by a pretty dashboard. We need a rigorous pipeline to verify every model before it goes live. The validation pipeline starts with clear requirements and success criteria. We then move through data quality assurance, stress testing the model, running a field pilot in parallel with existing systems, and finally, a controlled release with full governance in place. When measuring performance, focus on the metrics that matter for a plant. Precision and recall tell you how often the model is right and how much it misses. Lead time tells you if you have enough warning to actually act. Above all, we must measure actionability. Is the output actually helpful for a decision? Thresholds should be weighted by consequence. A utility pump can tolerate a high false alert rate, but a critical turbine cannot. We should tune our thresholds to optimize risk and response quality rather than just maximizing a statistical score. Field verification closes the trust gap. An AI alert shouldn't just say, check the machine. It should trigger a structured path of evidence gathering. The feedback from these field inspections is the gold that makes the AI smarter over time. We must design the alert-to-action workflow carefully. From a moment an anomaly is detected, through triage and work management, to execution and the final learning loop, every step must be documented and accountable. The PF interval is a reality of maintenance. AI only creates value if the warning arrives early enough to plan and execute safely. If it's too late, it creates urgency without control. If it's too early without confidence, it just creates noise. Validation must test for this action window. Data provenance is our source of truth. Industrial AI must show its work by referencing the specific historian tags or documents it used. If an AI cannot show its evidence, the recommendation must be treated as unverified. Validation must include abnormal scenarios like startups, shutdowns, and cleaning cycles. We also need to stress test the model against noisy sensors or missing data. We build trust by knowing exactly where the model is likely to fail. Finally, models should not live forever. We need to trigger reviews after major maintenance or process changes and define clear rules for when a model should be retired. A retired model should leave behind a record of its impact and lessons learned. In Part 5, we discuss how to operationalize this. Trust shouldn't be a slogan. It needs to be a management system integrated into the rhythm of the business. A board-level dashboard shouldn't just count pilots. It should show a risk heat map, assurance coverage, and value at stake. It should highlight which models need executive risk acceptance and show evidence of recent incident reviews and audit trails. KPIs for leadership should track model inventory, high-risk review status, and alert-to-action closure rates. We want to see how many alerts actually turned into verified actions and how much real value, in terms of avoided downtime or reduced risk, was created. Operationalizing trust requires a specific rhythm. This means daily reviews of critical alerts, weekly reviews of false alerts, monthly check-ins on model health, and annual reviews of the entire portfolio and risk appetite. When working with vendors, we must ask tough questions. What data was used for training? How is drift measured? Can it show evidence? Who owns the cyber risk? The AI must integrate safely into your existing CMMS and historian systems to be useful. We also need AI-ready engineers. These are professionals who still understand the physics of the asset, but can also challenge a model's output using field evidence. They're the ones who will translate a digital alert into a safe, physical work package. We must have a plan for model incident response. If an AI provides a hallucinated instruction or misses a critical alert, we need to contain the risk, investigate the root cause, correct the system, and publish the lessons learned to the risk register. Your AI risk register is a living document. It tracks every use case, the affected assets, the potential consequences, the controls in place, and any residual risk that has been formally accepted by leadership. Part 6 provides the implementation roadmap. Our goal is to build a foundation of trust before we try to scale toward autonomy. In the first 90 days, focus on inventorying every AI use case, even the shadow AI being used by individual teams. Classify them by risk, assign owners, and select one critical use case to redesign with a full alert-to-action workflow. Over 12 months, move from inventorying to classifying, validating, and governing. Do not scale the count of models faster than your assurance system can control them. Quality and trust must lead the way. When choosing pilots, look for clear business problems with quality data. Pick a risk level that's low enough to learn safely, but high enough to be meaningful to the business. Ensure you have the sponsorship to actually act on the findings. As you scale, prioritize the operating model over the number of models. Don't just replicate a model across plants without verifying the local data context and decision workflows. Plant teams must own the applicability on the ground. Finally, know when to say no. If the data can't be traced, if the output can't be explained, or if the organization can't act in time, the AI is a liability. Never let AI replace human accountability. Use it to strengthen it. In the final part, we'll look at case vignettes that highlight exactly where trust succeeds or fails in a real-world industrial environment. In our first vignette, a model repeatedly flagged a motor bearing that was actually fine. Because the model lacked operating state context, it mistook a normal process change for vibration. The lesson? False positives drain the trust bank and must be corrected by adding more context to the model. In our second vignette, a generative AI assistant invented a troubleshooting step that missed a critical isolation requirement. Because it had no source citation, the error was plausible but dangerous. The lesson is that AI guidance without source links must be treated as unverified. In our third vignette, a compressor failed despite a normal AI status because the model wasn't retrained after a major overhaul. This shows that model validity can change when a physical plant changes. AI review must be part of your post-outage readiness checklist. Let's consider a scenario. AI is 87% confident of a failure, but engineering sees no evidence and production is under pressure. Who owns the decision to shut down? This exercise highlights why we need predefined decision rights and clear standard for what counts as enough evidence to act. To summarize, board members should keep these 5 questions handy. They focus on identifying high-consequence models, ensuring independent evidence exists, and verifying that AI is truly improving decisions rather than just creating hidden risks. To move forward, we must stop treating AI confidence as proof and stop counting pilots as a measure of success. We must start classifying by consequence, requiring traceability, and integrating AI into our formal engineering sign-off processes. The key takeaway is this: industrial AI trust must be engineered and governed, not just assumed. The future isn't about AI replacing engineers. It's about engineers using AI within a stronger system of proof and accountability. Thank you for your time today. This presentation was designed for professional educational use, referencing key frameworks from NIST and ISO. All charts and data are authored for this session, and views expressed are intended to support site-specific engineering validation and professional judgment.